In addition to covering the last topic, as we just did, about whether an approximation to the curve is an overestimate or an underestimate, there are lots of different topics that we need to know for next Tuesday or Wednesday's quest. Here is the list of topics given to you so that you know exactly what to study. First, we covered finding the first and the second derivative implicitly. We also covered finding the slope at a given point. In addition to that, we've also covered finding the concavity at a point implicitly, concavity coming from your second derivative, okay? We also wrote the equation of normal and tangent lines implicitly. We wrote the linear approximation and determining if that approximation is an over approximation or an under approximation. We wrote the equation of vertical tangent lines and horizontal tangent lines. Remember, that means when your slope is undefined and when your slope is equal to 0. In addition to that, we're going to also have to be able to determine if a point is a maximum or a minimum. That is our second derivative test, and that is what we covered last class. All of these topics in total will be covered on your quest next Wednesday or Tuesday. I will help you through one more example here. While some of these examples may look a little bit longer, what they're actually asking you to do is fairly simple. In fact, each of these little steps here are walking you through how to answer the larger question. For example, if you take a look at example number 1 here, it says consider the curve given by the equation. Using the coordinate 4, 0, estimate a y value for the curve at x equals to 4.1. The first thing you would need to do to answer that question would be to find the slope of the curve, or to find dy dx. So as we move through finding dy dx, we're going to start with the first term here, x squared. Notice again, there are no y's in that term. So we're going to take the derivative normally as 2x because there's no chain rule necessary for the x. That would just be dx dx. We don't need that. We can move on to our next term here of y squared. And taking the derivative of y squared will give us 2y. However, remember that there is a y here, and y is a function of x. So we will need our chain rule here and multiply by dy dx. Once we're finished there, we can move on to the next term. Take the derivative of negative 2x. That is just a negative 2. Again, there's no y's, no need for the chain rule. And we can move on to the next term here of 4y. So that will be plus 4. Don't forget your chain rule for that y, dy dx. And then last but not least, that final term has a derivative of 0 since it's a constant. Don't forget to keep your terms with dy dx on one side, the other terms on the other. So moving things over, we have 2 minus 2x is equal to 2y dy dx plus 4 dy dx. And again, just simplifying by dividing out your dy dx. We're left with 2y plus 4 is equal to 2 minus 2x. And therefore, dy dx is actually equal to 2 minus 2x over 2y plus 4. First step would be to find the derivative. Now that we have the derivative, we can write the equation of the tangent line at the given point. Remember, the tangent line's slope is just given by your derivative. So we know that the derivative here at that given point, so at the point 4, 0, that's going to be 2 minus 2 times 4 divided by 2 times 0 plus 4. 2 minus 8 is negative 6 over 4, or this will just be negative 3 over 2. We're going to take that slope and just put it right into our equation. We'll have y minus 0 is equal to negative 3 over 2 times x minus 4. You can clean that up a little bit more, and you can just write that as y is equal to negative 3 over 2 times x minus 4. Once you write the equation of the tangent line, You can then approximate the y value at 4.1. Y will approximately be negative 3 over 2 times 4.1 minus 4. That simplifies to negative 3 over 2, or negative 1.5, negative 1.5, times 0.1. That will just be a negative 0.15. So that means that at 4.1, when x is 4.1, the y-coordinate is approximately negative 0.15. Not exactly negative 0.15, but approximately. The second question is asking you to take the equation of the tangent line that you wrote and determine if the value that you found was an overestimate or if it was going to be an underestimate. If you want to determine if something is an overestimate or an underestimate, first thing that we need to do is to find the second derivative of the function. Note with the first derivative being given by 2 minus 2x over 2y plus 4, we can use that to find our second derivative. Note that the second derivative here is actually going to require a quotient rule. Our second derivative will start with the lower function minus the derivative of the higher function, that will just be a negative 2, minus the higher function, the one in the numerator, 2 minus 2x, minus the derivative of the low. Here, the derivative of the low is going to be 2 times dy dx. Notice the 4 is a constant, so it doesn't have a derivative other than 0. And that will be all over low squared. So this would be all over 2y plus 4 squared. For our purposes, because they're not asking for dy dx in terms of x's and y's, we're actually going to leave it here because the whole point for now is to actually utilize that value to find the concavity. I just need the sign of the concavity. So once I do find the second derivative, I can actually move on to the next part. It says determine the concavity at the point 4, 0. If I want to know the concavity at that point, we're going to use the value for x and the value for y and substitute it into the second derivative. So that means that if I want to evaluate the second derivative at the point 4, 0, what we can do is this. We can say, all right, I'm just going to move those points down so we have a little bit more room. We can say that we have 2 times 0 plus 4. That'll be times negative 2 minus 2 minus 2 times 4 times 2, and then times the derivative at that point. If you remember, we actually did that before. That's right up here. Remember, we already found the derivative at that point. So we can actually take that value of that derivative at that point, which is negative 3 over 2, and substitute it right into the second derivative right there. So that'll be negative 3 over 2. That'll be all over 2 times 0 plus 4, that whole thing squared. All we need to do is now evaluate this expression here to determine what the concavity is, if it's a concave up or concave down. So if we start to evaluate, we now have 4 times negative 2 on the first term. That is a negative 8 minus, we have 2 minus 8, that's a negative 6, times these two terms here now. We have 2 times negative 3 over 2, that will be a negative 3, and this will be all over 4 squared, which happens to be 16. We just need to finish cleaning this up now, though. We have negative 8. This will be minus 18 all over 16. That is a negative 26 over 16. Even though we have the value here, what we're more interested in is the concavity. What is the sign of the second derivative? Here, our second derivative is a negative number. It's negative 26 over 16. Since it's negative, that means that our graph is concave down. Since our graph is concave down, it's going to look something like this, and that would mean that anywhere where the equation of the tangent line is written, as long as it's concave down, that tangent line will produce, again, an overestimate. So the number that we found, the negative 1.15, that is an overestimate of the actual coordinate on the graph. The question here that I'm asking you is this the only possible value for y if x is equal to 4? Hint, I'm asking you to look at the original equation. If you're looking at this question, you may be saying, what are they asking for? Is this the only possible value for y on the graph if x is equal to 4? Remember, when we deal with implicit equations, in this case, x squared plus y squared minus 2x plus 4y equals to 8, okay? Notice that this doesn't have to be a function. It's very possible for this graph to circle back on one another, possibly looking at something like this. So if we have x equals to 4, yes, we might know that if I plug in x equals to 4 and y equals to 0, the point that we had before, that's definitely a point that's on the graph. What they're asking, though, is there another point where x is equal to 4 where y has another coordinate? Well, one way to determine if there does exist another possible y value when x is equal to 4 is to take your original equation and substitute in x equal to 4. See if it produces another y. If that's the case, that would be 4 squared plus y squared minus 2 times 4 plus 4y is equal to 8. If that's the case, we can continue here. We have 16 plus y squared minus 8 plus 4y equals to 0. If we continue through, we have y squared plus 4y plus 8 is equal to, whoops, that wasn't a 0, that was an 8. Plus 8 is equal to 8. That would mean that we would have here y squared plus 4y equals to 0, which if we continue solving and we factor out a y times y plus 4 equals to 0, you will get y equals to 0, but also y is equal to negative 4. That means that this isn't the only possible value for y, the 0. Yeah, you can get that 0 here, but you also have to remember that there's another possible value for y. That's going to be y equals to negative 4. You could be asking yourself, well, how could this work? Why could y also be equal to negative 4? Well, if you take a second and if you graph this equation into Desmos, you can actually take a look at the graph itself. So if I'm going to go back and I'm going to use my Desmos app here, and I'm going to have x squared plus y squared minus 2x plus 4y equals to 8, right? That should be our equation there. Notice if I graph the equation of x equals to 4, right? That vertical line there. Notice that was the original coordinate that we were finding the estimate of. When we were looking for the coordinate for x when x was equal to 4.1, notice that that's a little bit further over on the graph. If I move it over and I move it out, notice where the blue line, that's your 4.1, intersects the curve, that is actually happening at negative 0.159. That's really close to the negative 1.5 that we found. In addition, notice that this value, negative 0.159, is below negative 0.15. That means that the value that we found, right, was a overestimation, right? an overestimation because negative 0.15 is above negative 0.159. So we actually found an overestimate to the actual value there that you can see. Okay, so again, if we're taking a look and just coming back to this idea of is there another y value for the original graph at 4, 0, there's also one there at 4, -4. So 4, 0 might have been 1 point when x is 4, but it's not the only point. And again, just reinforcing here, when we have that value that we approximated, it was an overestimate. It was over the value of the graph. I'm hoping, gentlemen, that as we went through this and as we looked at the graph and kind of pieced it all together, that helps you really study here for implicit differentiation. If you have any questions going forward, please feel free to reach out to myself or to Dr. Summers.